Hello everyone. Welcome back to Palance AI and welcome back to the Deep Learning Foundation series. In the last video, we learned how AI models measure their mistakes using something called loss functions. Today we go one step deeper. How do these models fix those mistakes? You and we're humans. How do we learn? We learn, of course, by course correcting. We try something, fail a little, adjust, try again. Whether it's learning to ride a bike, solving a math problem, or in my son's case, he's currently learning soccer, it's always about we try something, right? Slowly improve by feeling the difference between what we thought would happen and what actually happened. Deep learning models almost work the same way. They make a prediction, compare it with the actual answer, feel the slope of their mistake. Again, if I can repeat, they make a prediction, compare it with the actual answer, feel the slope of their mistake, and then adjust the weights to get a little smarter each time. And that pretty much sums up the entire learning process, and that's called gradient descent, the topic of today's video. If you have ever wondered, how does a model actually update its weights? What does taking a gradient mean? I know it's mathematics, but intuitively, what does it exactly taking a gradient mean? Why do people care so much about learning rates and optimizers, like you might have heard these names, Adam, RMSProp? What are all these? And how does a neural network or a deep learning model with millions of parameters gradually navigate towards the right solution? All these AI models, the LLMs, the core idea is the same. It's gradient descent. So that's exactly what we're going to learn in today's video. There is some math, but please don't worry too much about the equations. Some of us nerds, like to see the math. But please focus on the big idea. Gradient descent is the compass that guides a model from random guesses towards intelligence. All right, too much talk. Let's jump in to see how the gradient descent actually works in action. Let's talk about gradient descent method. So what exactly is gradient descent? Well, whatever the optimizer we may use, when we're trying to build deep learning models, either in TensorFlow or PyTorch, right? All these optimizers are based on gradient descent method. Again, we use the optimizer, right, to minimize the cost function and update these weights in an iterative fashion. Okay, so let's take a closer look at the gradient descent method. We have already seen the equations, right? So we update the weights, W, and also the bias term. So alpha is something called a learning rate. It's a hyperparameter. Okay, so we're going to take a look at it very closely. So J, again, as you know, is the cost function, right? The cost function is the penalty which the model is paying, right, if the weights are not optimal. So at the beginning, what the algorithm tries to do is randomly initialize these weights. Okay, so for those randomly initialized weights, right? So for these randomly initialized weights, let's say the first set of weights, the pink weights, right? We use the randomly initialized pink weights. We use the x1 to x8 for 784 pixel values, right? And then we compute the outputs in the hidden layer, the A1 to A512, right? Then we use the outputs in the hidden layer, A1 to A512, and the blue set of weights, W2, right? To compute the ypred, right? The 10 units in the ypred, the final output layer, okay? So then this ypred, we compare with the actual y, we get the loss, right? For each image, we sum up all these losses and we divide it by the total number of images and we get the cost function J, right? Then for this cost function J, we take a partial derivative of this J, right? So we take the partial derivative of this J with respect to each parameter, each weight, right? Remember, in the previous, one of the previous videos when we talked about the weights, right? So for this simple two-layer neural network, right, which we discussed, the total number of weights or parameters, right, which were about 400,000. So the algorithm will be taking the partial derivative of this cost function with respect to each and every parameter of this 400,000 parameters, right? The total weights. And then you take the partial derivative, or basically you calculate the gradient with respect to the cost function, and then you multiply that with a hyperparameter, this is actually called learning rate. You multiply by that, right? And then you use this term to update the weights in iterative fashion. Okay, you do the same thing for the bias term. Again, both the weights W and the bias term together are called the parameters. Okay, so this is the math. What about a deeper, intuition? What exactly is happening here? So imagine that, on a cloudy day, you're trying to climb down a mountain and you're trying to reach the bottom of the valley, right? It's very foggy, you can't see clearly. So what do, right? You try to come down the valley, right, by just feeling the slope beneath your feet, right? That's what you try to do. So imagine now I have drawn here like this cost function as a function of the weight parameter. Now remember, as I said, the weights, like for the simple two-layer neural network I talked about, right, we have 400,000. For more recent latest AI models like language models or computer vision models, your total number of weights might be like even a billion, right? More than that. So imagine taking the partial derivative with respect to every one of those weights. Since we cannot visualize that, right, taking the gradient in so many dimensions, this figure here just shows you just like a sample cost function, right, as a function of just one W. Okay, just bear with me so that you can understand the intuition as to what's happening. So now again, as I gave you the analogy of climbing down the mountain by feeling the slope, right, it's very similar here. So whenever you take a derivative or a partial derivative of j with respect to w, that's nothing but calculating the gradient at that particular w. So you calculate the gradient of the cost function, which is nothing but feeling the slope. Think of it like feeling the slope, right? And you use that to determine how much you need to update your w. You started with some random weights in the beginning stage, right? So you start with some random, calculate the j, the cost function, take a gradient of j with respect to that, the w, and then you use that to get your next w. Okay, so in essence, what you're taking is you're taking small steps, right? You're taking small steps and you want to go to this minimum j, where the cost function is almost all zero. So if you can go there, you can say that, right, your model has learned your weights have become optimal. So you start like this. You start with some randomly guessed weights and you slowly, take baby steps, and you keep going until you reach, this green color here, which shows you the minimum, cost function. Basically, you want to calculate or update the weights in iterative fashion in such a way that ultimately j goes to 0. If j goes to 0, that means you have learned the optimal weights. And once you have learned the optimal weights, you can say that your model has become smart, right? It has become learned. And, any new prediction tasks you give it to the model can do, pretty amazingly. Okay, so this is how, a gradient descent method works. Again, the image I have shown you is with respect to, the cost function I have plotted with respect to just one W, one parameter. First, let's talk a little bit more about this parameter, right, called alpha. So because I said it's a hyperparameter. Hyperparameter means it's something, developers like ourselves, when we're trying to build deep learning models, we can tune it. We can play with it. So what kind of alpha learning rate or alpha can we choose? Okay, so let's talk about that. Again, in literature, sometimes this learning rate is also used by different symbols, like, sometimes it's eta. Eta also sometimes represent the learning rate, but alpha is also used. So I've just went with the alpha. Okay, so again, these are the equations which we use for the gradient descent method. So let's look at the situation where the learning rate is too small. What happens? Okay, so again, this is our cost function. I have plotted the cost function with respect to just one parameter w so that we can understand the concepts here. Okay, so again, the goal is to reach the minimum j, right? So, but if the learning rate is too small, so what happens is the updates, the weights are very, very small, very, very minimal, and it may take forever. It could be very, very slow, and it may take a long time to reach convergence. Sometimes we may stop early, right? So that's the drawback here. If its learning rate is too small, you may never converge. I mean, it's going to take forever. But if learning rate is too big, then what's going to happen? Well, if learning rate is too big, as you can see here, you may still not reach convergence, because in fact you may diverge. The algorithm can, shoot around the minimum and very quickly start diverging. Okay, so the key is to find an optimal learning rate alpha, right, which can ensure, right, a good convergence, and you can reach the minimum. So you can find the optimal W, which can minimize the cost function. So how do you select this alpha, right? So this is, again, there's no science here. It's again empirical. So it's based on practice. So practitioners have found that, like, there are different alpha values can work for different types of problems. Typically, sometimes you can start with a bigger alpha, but gradually you can decrease it in an adaptive way. There is something called an exponential decay. So the different ways you can tune this learning rate. Right? In the later videos, when we do the hands-on projects and build deep learning models, I'm going to discuss some of these ways as to what kind of learning rates we can use. Okay. Also, one more observation. If you see in these figures here so far, when I plotted the cost function as a function of, parameter W, most of them look like nice balls where you have nice nice proper minimum J, right? Well, in many situations, the curves may not look like that. Right. In fact, you may have all kinds of mountains, ridges, plateaus. The shapes can be very different like this. So, for example, if your cost function looks something like this, and if you initialize your weights in such a way that you start on the left, right? If you start on the left, you may reach a minimum, but it may not be a global minimum. It could be something called a local minimum, which is okay, but it may not be optimal. Similarly, if you initialize W in such a way that you start on the right, you may reach something called a plateau, again, taking forever to reach the global minimum. So again, as I alluded earlier, you just have to play with it. You just have to be, tune this alpha. It depends upon the problem, but also it depends upon the different kinds of optimizers which we can use. Some of the optimizers are more sensitive to this learning rate. Some of them are not. So let's take a closer look at what are the different types of optimizers. These are basically different variations of the gradient descent method, which we have already talked. So you have a good understanding, right, as to how these optimizers work already. But there are some slight variations, each trying to overcome the limitations of the other optimizer, right? So again, if you please don't get intimidated with all these equations here, I want to give you a list of some of the important optimizers that are being used, by different researchers and practitioners. So for example, stochastic gradient descent, right? As we discussed earlier, by default in TensorFlow and Keras, this would be the mini batch stochastic gradient descent. It is slower, but it ensures good convergence. But we have to fine tune this alpha, learning rate parameter alpha. Typically, it's a good choice for simple problems. Okay, so if you're learning deep learning, starting with it, you can use the SGD, and by default in TensorFlow Keras, it defaults to the mini batch stochastic gradient. Okay, so then we have an optimizer called momentum. Okay, so this momentum tries to overcome the limitations of SGD, which is very slow. So it tries to speeds up convergence, and it does that by using the gradient as an accelerator. Okay, so what momentum does is it keeps track of a previous gradients, whereas stochastic gradient descent only focuses on calculating the gradient at that particular W, meaning only focuses on local gradient, whereas momentum keep tracks of previous gradients. So it calculates the gradient at a particular W and it subtracts it from the momentum vector. Okay, don't worry too much, if you do not understand all these equations at this stage, but if you want faster convergence, so think of using momentum optimizer. You may have an extra parameter here called beta. Okay, now then there is another optimizer, again optimization algorithm, Nesterov accelerated gradient method, right? This again tries to overcome some limitations of momentum, but in essence it calculates the gradient. Instead of a W, it calculates a W plus beta m. It's a little bit faster than the momentum, reduces oscillations, right? And we can use it, when we want even more faster convergence. Then you have AdaGrad. So what AdaGrad does is, because sometimes, like, in deep learning, when you have not properly normalized your input data, right, the gradient descent method may try to reach the optimum in a convoluted way. So this algorithm tries to make the gradient descent go to the minimum in a more direct route. Okay, and for that, what it tries to do is it scales the gradient vector along the steepest dimension. Okay, but the problem with this AdaGrad is the learning rate can get scaled down too much. With that being, the weights are really not getting updated that much, and it may not even converge. So it is used for some simple task, but for deep neural networks, AdaGrad is not that much used. Okay, then you have RMSProp. This is also a preferred algorithm for deep learning research. It tries to overcome the limitations of AdaGrad, right, by accumulating only the gradients from recent iterations. Okay, it has one extra parameter rho. But again, RMSProp is one of the preferred algorithm for deep learning research. Many people use it. And then you have Adam. So Adam combines the best of momentum and also RMSProp. Okay, as you can see, there's a bunch of equations here. I'm not talking too much about these equations because at this point I don't want to confuse too much math. Again, at least we need to know on a very high level which algorithm to use when. Okay, so with Adam, again, we don't have to significantly tune the learning rate. A default value of like 0.001 is good. Again, it's very popular due to its efficiency and adaptability. Okay. So this is a brief overview of the different optimizers. Again, they are all variations of gradient descent method. Now, if you're wondering how are we going to implement this, right? Well, that's pretty straightforward. So when it comes to building models in TensorFlow, Keras, and even PyTorch, we are not discussing PyTorch here, but it's very simple. You, for example, in TensorFlow and Keras, you just simply say import TensorFlow STF. And then if you want to use SGD optimizer, you simply say tf.keras.optimizers.sgd and you give a learning rate. If you don't give, it chooses the default learning rate. Okay. Then similarly, momentum, you have a similar syntax here for NAG or RMSProp or Adam. Bottom line, whether it's optimizers, as you see here, right, or the loss functions or the activation functions, we don't have to manually implement the math behind these equations or these methods, right? All these are pre-built in TensorFlow Keras. It's just us knowing which to use what, right? What activation functions to use when, what loss functions to use, and what optimizers to use. Okay, so if this all seems a little bit high level, right, and complicated, please don't worry. Focus on the intuition, focus on the concepts, and once we start doing hands-on projects, right, that's when you'll see much more clearly as to how easy it is, how simple it is to use any of these activation functions or loss functions or optimizers that we have discussed so far. Okay, hopefully this video helped you finally see what gradient descent is actually doing. It's not just an equation, but the core learning engine behind every modern AI model. Whether it's a neural network recognizing images, or a massive language model, or an LLM with billions of parameters, the idea is the same. Take a small step, learn from that mistake, update the weights, repeat the process. If this video made sense for you, then you're already way ahead of many beginners in their AI journey. Because many of us, use AI without knowing how these AI models actually work or actually learn. So hopefully these videos are helping you to see how the AI models actually work under the hood. In the next video, we're moving into one of the most important and exciting ideas in deep learning, and that's called convolution neural networks, or CNNs. In fact, CNNs are the ones which originally brought glory to the deep learning and made it the face of modern day AI, long before the LLMs and the transformers, which we keep hearing, in case you hear about it. But that's for another video. If you like a complete structured curriculum with hands-on projects, you can also check out my full deep learning mastery course on Udemy. I have linked it in the description below. But again, if you're new to this deep learning series, I have also included the link for the full playlist in the description. Please check it out. Thank you so much for watching. And if you're learning something valuable from this series, please consider subscribing so that you don't miss the next valuable lesson. Thank you so much. Happy learning.